Hello, welcome and good morning. This is session number 89 on the value of community data in the design, testing, selection, and maintenance of casters. My name is Clyde D'Souza. I'll be serving as the moderator for the session, and assisting me is Julie Harrison. Before we get started, please remember to place yourself on mute. You can post your questions in the chat window during the presentation, and our presenters will address them at the very end of the session in the final 10 minutes. During that time, I will also be providing you with the CU code for the session. I will now go ahead and turn it over to our two presenters. We have Anand Mhatre and Jack Fried. Anand, I think you're going first, so please take it away. Thank you.
Thanks, Clive. Good morning, good evening, and good afternoon to everyone based on where you're joining from. I'm Anand Mhatre. I am a faculty at the University of Pittsburgh, and my research is on design, validation, and maintenance of wheelchairs and some assistive technology. And today I'm joined by Jack Fried. Jack, you want to introduce yourself?
Absolutely. Yeah, good morning, everyone. My name is Jack Fried. I'm a graduate student here at the University of Pittsburgh studying rehabilitation technology. I did my undergrad at Pitt as well in mechanical engineering. And I joined the master's program in fall 2020 and started doing research with Dr. Mhatre on what we're going to be presenting today. So I'm very excited.
Thanks, Jack. So a quick shout out to the sponsors of this work. So we have national and international funding agencies that are sponsoring some of this work. So the agenda for today, we'll go over the background or the motivation for this work. We'll then look at some of the community data sources which are providing data for some of the work that we have done on casters. The work has focused on casters, but this can be applicable for other parts of a wheelchair and the whole wheelchair as well. We'll then take a look at how this data is helping us improve caster quality, design, and then some of the part selection for casters. And then we'll look at how we can support preventative maintenance services with the community data and some of the data that has come from other parts, that is quality testing and design. And then we'll take a look at future work, what lies ahead of us. And this should be about 45 to 50 minutes, and we'll give 10 minutes for Q&A later on. So learning objectives for today, we want to examine if evidence-based strategies and wheelchair quality testing protocols whose outcomes have informed 4 areas, that is design, testing, selection, and maintenance of wheelchairs, wheelchair casters. We would like to analyze community evidence gathered from several unique sources and then discover six sources developed from community data and testing protocol findings, that is from all of our work. So the background, we have about 4 million wheelchair users in the United States, but 80% of people with disabilities, they live in low and middle income countries. So about 75 million or so are people having wheelchairs that are required, and about 20 million of them are provided. But if you look at some of the wheelchairs that are provided in the United States, we see a lot of variety across the devices. We have tilt-in space, we have ultra lightweight wheelchairs, standard wheelchairs, power wheelchairs of all sorts. But I realize that there is a big problem with wheelchair devices and some assistive technologies that are in the locomotor assistance space. And that is, wheelchairs break down frequently with very little use. If you look at the failure rates that are collected over a 6-month span, we see that the failure rate has doubled or even tripled over a space of 15 years. So it goes all the way from 26 to 88% based on research evidence. And so these are studies that have collected failures in the community with manual and power wheelchairs. Now, what fails the most among wheelchairs? We'll see that the rear wheels and the casters, so these are front casters and rear wheels, they constitute about 50% of all wheelchair part failures. Casters alone, they are about 1/3 of all wheelchair failures. Now, when these rolling elements, or I see that rolling supports, when they fail, there is a big consequence ahead. It can tip the wheelchair and the user can fall out of the chair and get injured. Now, that is not the only consequence. There are several other adverse consequences. For example, the user can get stranded in the street if a failure happens. Otherwise, we have also seen that repairs take a longer time to happen. And there is a lot of, we have known a lot of things that happen after a breakdown, which is we need to go through the prior approval process. You need to get the parts, you need to contact the client contacts you, of course. You need to go to the client and then make the repair. But that takes anywhere between 1 to 6 months to happen. And that's where the client may lose access to work, access to pay, access to work, access to school as well. There are those adverse consequences. We have found through research that 1/3 of all wheelchair failures are resulting in these adverse consequences. And since repairs are hard to come by, the user may have to stay in the bed or a regular chair. And that is where research studies have found out that there is a larger association between breakdowns and failures and pressure sores and hospitalization. Now, as I said, wheelchair breakdowns is a big problem. Now, to remedy this problem, there are several areas in which work needs to be done across many of these areas, and some of these areas could be in the area of user interventions, user training, could be in environmental interventions. My work is focused on device performance, and this is specifically the wheelchair product, and majority of it has focused on wheelchair casters, and it has done in 4 different domains. And I think these are the most important when it comes to device performance. First one is quality, or what is the durability and reliability of a device, which is mostly determined by the testing methods that are there in the wheelchair area. Then design is another one, which is really how do you design a wheelchair? What are the different parts? Then maintenance is another area, and then that is followed by selection. So we'll go into each of these areas and see how community data has helped us develop new research and new findings in each one of them. So before I dive into those areas, I wanted to talk about some of the data sources that has helped this work. So we have focused on casters, but as said before, this can be applied to other wheelchair parts or even the whole wheelchair, as we have done in other research areas. So the first failure data source is the caster failure data. And so when I say caster failure data, this has come largely from a wheelchair repair registry. This repair registry is developed by technicians who go out in the community and do repairs. This is the registry has come from about 60,000 or 65,000 repairs that have happened in the community, and the technicians have used a software called as Labor Tracker that has been developed by US Rehab and VGM, and that software was used to collect data, and those data points specifically are, you can look at the failure modes for different casters or different types of casters across different wheelchair models. You can look at the time to failure, and you can also look at location of use. So those are 3 important data points that came from 65,000 repairs. Then we have some validated tools, and these have come largely from research. And so we have the CFIT, that is the caster failure inspection tool, that was validated at the University of Pittsburgh, test, retest, reliability tested. And so we sent this tool to 3 wheelchair repair centers in Indonesia, Mexico, and one in Scotland, and we got failure data from there. Again, this failure data was about failure modes, time to failure, location of use. There is a wheelchair components questionnaire that is developed by Karen Rispin, and we got some data from there. That's largely from Kenya and some other places. And then we also collected failure samples. These are samples, for example, you're seeing on the right hand side, where there is something that has broken in the community. So we have got those failure samples as well here in the University of Pittsburgh, so we can analyze them and do some development. I want to talk about caster usage data or wheelchair usage data. So what is this data? This data includes data points on how a wheelchair is used or how it wears down in the community. So data was collected on road shocks and vibrations, largely by accelerometer devices. You can see on the right hand side that there is a black box that's there on top of a caster that contains an accelerometer and a battery. Other data was collected on uh, environmental factors, for example, humidity. So humidity, we know that in tropical areas that, and again in coastal areas where humidity is high, um, that's where we see that there is a corrosion of a lot of wheelchair parts, and that affects the durability of these parts. So we have collected data on that. On the other hand, there's another thing which is tire wear down, and so abrasion or rough surfaces, rough terrain is a big problem. It's just not a big problem in low and middle income countries or tropical areas, but it is also a big problem in the rural areas of resource settings where you don't have pavements and you have to drive on roads, or and roads can have potholes. So we have also collected data on tire wear down, as to how tires are reducing in thickness, and how they are etching and how they are cracking in different parts. Some of this data collection has happened in several different areas around the world, and in Pittsburgh as well, and in the United States as well. And lastly, there is another data point that we collected, which is about caster servicing or caster maintenance. And so these are preventative maintenance events. Specifically, these are service events. If you've been in the wheelchair world, we know that preventative maintenance is not covered by insurance. So when have these events happened? These have happened when service has happened for other wheelchair parts. For example, a wheelchair brake is being repaired or the battery is being repaired, and that's where the technician sees that, hey, the caster is not doing well, so let's service the caster. And so these are some of the events that have happened in the community, and we have collected these servicing and replacement events for caster parts. So these are the three important data sources that we have used for developing new research and new evidence in the areas of quality, design, maintenance, and selection. So let's look at how this data has helped with developing testing methods, new testing methods in the area of wheelchair caster quality. So I want to talk a little bit about quality testing standards. So there are international standards for wheelchair quality testing, where the wheelchair is put on fatigue testing machines. It is bearing the load of a test dummy, and that's how the wheelchair is being tested for some test cycles. But one of the big things that I've found with these testing standards, and I should not say one, it's two. First one is that these testing standards, they do not simulate outdoor conditions, and that is why the big thing that happens, the problem that happens because of it, is that the failures that you see outside in the community, in adverse settings, I should say, that you find in rural settings, in resource countries, and in the low and middle income countries, you don't see these failures on these testing standards. And secondly, one of the big things with these testing standards is that we do not have specific standards for adverse environments. And that is why I started with a new testing area or testing research for developing caster standard. And so the big research question when I started was, can we replicate these failures that you see in the outside world in the laboratory as well? So we started with shock data collection, as I mentioned before. These are some of the shocks that you see in adverse environments. My next step was to filter these shocks that we see and understand what causes fatigue of a caster assembly. So I had these shocks go through some bending moment analysis and bending stress analysis. I'm not going to dive deeper into this. And then I developed a community shock profile based on this data collected. Now I had to replicate this shock profile in the laboratory environment. That is where I developed a caster test system. Now, what is this test system? It essentially is a giant record disc player that has a couple of obstacles on it with standard heights, 1/2 inch, and it has casters that are mounted from an arm under a known load. And so these casters are hitting these obstacles and they are getting tested. With this validated test system, there is a lot of experimentation when I say validated. behind this, but these obstacles, they are standard heights, and I wanted to know how can I replicate the community shock profile on this one. So the next step in this process was I put accelerometers or sensors on this caster testing arm, and I developed several different obstacles layouts. As you can see, there are several different layouts, and there are different sizes or thickness of these obstacles as well. So I did several trials, experimented what can help us develop a shock profile on the caster test that is matching the community profile. After matching these shocks, what we found out is that if you want to simulate 1 year of wear down of caster models in the laboratory, you have to include one obstacle, which is 3/4 inch obstacle and 1500 rotations of that, plus 2 half-inch obstacles with 4500 rotations. And that will simulate 1 year of wear down in adverse settings for casters. Now, once the shock factor was done, we know that corrosion is another one, which is corroding caster parts, and we know that this needs to be included based on failure samples that we collected into the shock testing protocol. So how was this simulated? Like, I developed the caster test system for shocks. For corrosion, we bought a big salt fog chamber that bakes the casters in a salt fog, and that is supposed to be done for 200 hours. Now, the 200 hours is something that came up with some experimentation where we collected humidity data and we matched with the humidity rate that happens in this chamber. But I just want to put it out directly that this is 200 hours of baking in the salt fog for casters. On the right hand side, you can see that tower in the middle. That is the thing that shoots this salt fog, or makes this salt fog in the salt fog chamber. This is some experimentation which I did with mass loss test panels to understand what that humidity rate looks like, or how much time do you want to put these gases in the salt fog. And then there was another factor that I was mentioning. It's tire wear down. We know that rough environments that are there outside. So we wanted to simulate this on the caster test system. And so for that, I put a sandpaper on the caster test system, and the next step is to understand what's the grade of that sandpaper, what's the grit size on the sandpaper. We really wanted to understand what do we put. So we, based on the caster failure samples that were collected and new samples of the same model, what we did is we calculated the reduction in thickness and in how much time that has happened, and based on some experimentation with different sizes of grit grades, we found that a 30 grit sandpaper would be very helpful to simulate the tire wear down that you see in a year, right? Because we wanted to pair that with the shock testing protocol. So a 1 year of tire wear down was simulated through experimentation, which I don't want to go into or dive deeper into. Once corrosion and abrasion were simulated, did a short experimentation to really understand, are these two factors affecting caster durability in the laboratory? There was some comparative testing studies. I don't want to spend a whole lot of time on this. The results of this study were very significant. We found that with the caster models tested, 47 to 100% reduced durability due to corrosion, and 13 to 63% reduced durability due to abrasion. One of the other findings, I think this is the most impactful, that is 2/3 of models, they saw failure modes that changed from low risk to high risk because of presence of corrosion and abrasion. And that was really the driving factor for including the corrosion and abrasion in the shock testing protocol. Now, how did this go for casters? We first simulated corrosion in the salt fog. That was followed by shock and abrasion testing on the turntable. And so this cycle went on until the caster breaks. This is final testing where we had 6 caster models, 2 samples per model. And while testing was going on, we collected community failure data collection with the CFIT tool, with the WCQ tool that I mentioned earlier. And so these are some of the caster failures that we collected for some of the casters we tested. And so to address this question, that can a lab-based testing protocol reproduce caster failures that you see in the community? And so if we look at these three models, model A, B, and E, we see that these failures can be reproduced to some extent. And so we see the tire failure, the wheel fracture, the fork bend, or a loose hub. And so we did get these promising results from this initial testing. And we thought, can we build further on this now that we can replicate these caster failure modes rather. And so the next experimentation, which I think I would like Jack to explain, where it started from the registry related data, and how did we go ahead and test or replicate some of these failures as well as time to failure. So building further on the research that is conducted, how did we build further, and we also simulated time to failure on the caster test. Jack.
Right, yeah, thank you. So, right, now that we have this kind of lab informed testing procedure, we wanted to kind of look at what trends we could identify from this large data set, which I think ties nicely into the keynote from yesterday. Analyze this large data set, find the trends, and from there inform testing, design modifications, and selection guidelines. So we took a look at the data we had, again, 60,000 total repairs. Over 6,000 of those were caster breakdowns. 151 of those were actually caster-related service repairs, what Dr. Mhatre talked about before, actually fixing the components of the wheelchair before they cause some actual high-risk harm. And so we were able to make a few discoveries here. One was using one manufacturer's Tilton space, which had 219 failures, and their ultralight, which had 485 failures. You can see in these pie charts that the green and the yellow, those are your low risk failures, your worn out tire, your bearing failure, where the caster can be replaced safely without causing harm to the user. And the high risk failures, which is your wheel cracked, your bent bolt and fork, both of those can cause immediate harm to the user and want to be avoided at all costs. And what we saw with the manual wheelchairs was that actually the Tilton space had double the amount of high-risk failures that the ultra lightweight experienced, which might be surprising to some people, based on, use case and whatnot. But we also saw, you can see here too, that there's a large amount of bearing failure, and the ultra lightweight, which Anand will talk about later when we talk about service and maintenance, had a higher rate of service repairs done to it. So one of the explanations could be, and he'll talk about this later, is that the bearing failures were caught and fixed and replaced before actual harm could be done to the caster, like a fractured bolt or something like that. The other thing we saw in the power chairs, which had a large amount of failures, over 1,000 for each of these, that as you move up the group number, so from group 2 to group 3 to group 4, and your complexity of your seating increases, you actually see a higher percentage of high-risk breakdowns. Increases pretty steadily from 10% from group 2 all the way up to 36% for group 4. So we also got to look at just group 3 HD across multiple manufacturers, and their failure distributions were very, very similar. So these might be trends that we could see across other manufacturers too. So what it's kind of telling us is that users who require a higher level of seating support and have more complex rehabilitation needs are at a greater risk of experiencing caster breakdowns that can cause user injury and other adverse consequences. So we wanted to kind of start addressing some of those issues we saw, whether it be through maintenance or quality testing. We can go to the next slide. So we also, as Dr. Mhatre said, looked at time to failure here. So looking at these, this is a Kaplan-Meier survival curve. It plots all of the total failures as a percentage for 2 of our manufacturers, and decreases that percentage over time as the casters fail. So this gets a sense of, the rate at which they fail. As you can see, manufacturer 4 here fails at a slightly faster rate than manufacturer 2. And you can also see the half-life is right about a year and a quarter, and none of the casters survive over 2.5 years here. So this gave us a lot of evidence on the rate of failure, as well as more validation to a lot of previously done, as we talked about, community-based studies. That said, most breakdowns are occurring between 1 to 2 years of use. Next slide. So now, now that we had these trends based on failure and based on how fast they failed, similar to what we did in the lab for correlating lab and community failures, we also wanted to correlate, see how fast they failed equivalently to what we saw in the community. So this is an ongoing study we're doing, and we're showing the preliminary results here. We ended up selecting 8 different models that we had basically enough community data on to track time to failure. So when the wheelchair was purchased, when the failure occurred, if it was their second caster, we could go from that first failure to the next, and actually see how long it lasted on the chair. So we chose 8 models across 3 manufacturers. And this was to correlate, what we're seeing in the lab to the community, so we can use the lab testing as a validated tool to test before you use products, maybe while the products are out, to see, their quality and their performance. So you can see some of the results here. We've done 2 tilt and space models so far. In the lab, the 6-inch model we tested, they all failed by worn tire. They lasted right about 5 years equivalent on the lab testing. And compared to the community data, the worn tire is actually the second most common failure behind bearing failure at 21%. And that time to failure is roughly 2 years. So there's just some discrepancy there. And along with the second model, that failed, all 5 models failed by cracked wheel at roughly 1.5 years equivalent. This was the most common failure for this model, 38%. And the average community time to failure for this one is 2.88. And you can see some of these failures in the pictures next to them. So we have some models that seem to be more accurate than others. And we're really interested to finish this study so we can get a look at all the different breadth of models that we have from the community compared to the lab. The other 6 models we'll be doing are all ultra lightweight. So that should give us a good idea of where we are correlated to those. So the next slide. So after this, the biggest thing is actually putting out some research outputs based on the sources that we've developed here. One of them is the testing protocol that Dr. Mhatre just spoke about. We're adding it, it's towards the end phase now of being incorporated into ISO 7176 to be included in the suite of laboratory testing for wheelchair standards. So soon this will be an international standard on how to test wheelchair casters and how to track their performance. So we're hoping that this information could get out so we can spread this and start testing casters on a more global basis. We also created the wheelchair caster fact sheet from PIT RERC that I'll be talking about in a little bit. These are just design considerations for users' needs and also the environment they'll be using the chair in. So this is really, really useful for not just the users themselves, but clinicians, policymakers, manufacturers, suppliers, really the whole breadth of the field can utilize this to make informed decisions on their caster selection for their clients. And we also came up with the ISWP design considerations for wheelchairs. The document was developed to create a guide for wheelchair designers, manufacturers, providers, users, caregivers on what design considerations you should consider when designing for wheelchairs in adverse environments. So it was a pretty high need identified by the standards working group of ISWP because the WHO guidelines for the provision of manual wheelchairs for less resource settings, it provides general guidance, but this was a document we wanted to create to kind of inform users of some of the pitfalls that are common when designing for adverse environments people might not be too used to. So those sources are listed down below, and even later I can link those in the chat there so people can just click on over to them. And so now we wanted to use this data to actually inform caster design. So if you can go to the next slide. We kind of talked about this a little bit before, and is that caster bearings fail very rapidly, especially when they're exposed to corrosion, because after that, the material is just subjected to rapid fatigue. And once the bearing fails, there's now that higher load that's exposed onto the fork and the stem, and a higher risk failure that's going to cause injury is much more imminent. So we wanted to see, if you can go to the next slide here. We wanted to see if we could actually create a bearing bushing design that would increase its resistance to corrosion, increase its durability, and was also cost effective. So in doing this, we decided to test thermoplastic bushing. So these materials were selected based on recommendations from wheelchair experts, from the ISWP Standards Working Group. Both of these materials you can see down here, the bottom two, were selected because of their self-lubrication, lower wear rate, low coefficient of friction, as well as resistance to corrosion and chemicals, and low humidity absorption. So the thought was, if we could actually make a design change in the form of a material change, we could create a bushing that's less susceptible to these factors and actually last longer in the chair. Because with the two bearing options we've selected here, you can see the standard double shielded deep groove caster ball bearing. These are low price points, but because they're just shielded, there's room for the humidity to invade the caster ball bearing, get in the actual balls of it, and kind of fail it from within and corrode the material. So these are really, really standard in adverse environments. And we wanted to see if an actual material change would be the appropriate way to redesign them. So we have these. We also chose a higher price point chrome steel double sealed deep groove caster ball bearings. So these actually had a nitrile cover that sealed the ball bearing so that it would be less susceptible to things like humidity and whatnot, and debris, dirt, things like that to actually infiltrate the caster. So we wanted to compare all these together and kind of see where the thermoplastic bushings lie in terms of durability, which we measured in cycles on the testing machine, and cost effectiveness that we identified as a cycles per dollar ratio. So if you go to the next slide, we can see here the failure modes that they experienced. So the standard ball bearings failed, all four models failed the same exact way, bearing fracture before 2 years of simulated wear. So this is very common. This is what we see often with this type of model of ball bearing. I should say we also use the same exact caster model, which is a caster model that's often used in low resource settings or any adverse settings to just control the performance of just the bearings bushings. All four models failed this way. The chrome steel option, 2 of those models passed the 6 years of testing we capped it off at. And 2 of the models failed similarly to how you can see there below. Really, really intense bearing wear that eventually led to bent forks and bent wheels that eventually made the caster fail. Both of the thermoplastic bushings, 2 of those models survived the full 6 years of testing, and 2 of those models failed the way pictured below through stem failure. So you can see that stem has completely separated at the beginning of the fork. Both models failed this way, and there was some failure of the bushing at the flange there. So we wanted to not only see the failure modes, but how well they actually performed. And if you go to the next slide, there's a lot of information on this graph, but it kind of tells the full picture of the study. So as you can see, the thermoplastic bushings are the yellow bar graphs, and they're compared to the number of test cycles on the left. The thermoplastic bushing number 2, on average, performed the best out of all of them. And the thermoplastic bushing, the first one we tested, also performed really well. In terms of significance, thermoplastic bushing number 2 was significantly more durable than the standard shielded bearings. As you can see, the double shielded bearings failed, as I said before, below the 2-year mark, right below it, and had a very varying, as you can see in the black, a large variance in the performance of the different models. So in terms of the cost effectiveness, which is the orange lines there, which is compared to test cycles per dollar on the right, this is actually really where the biggest difference comes in. Because of that big price point, even though the double sealed bearings perform very well, the cost per dollar is, the cycles per dollar is just not adequate for realistic use. However, the bushings actually had the highest amount of cost effectiveness. Both bushing models were significantly more cost effective than those sealed bearings, and also had higher cost effectiveness than the double shielded bearings. So this is one example of how we can show through this testing that design changes, whether it be through material or the actual design of the caster materials, can actually improve caster use in the environment. And so we can go to the next slide. So this is the application of data for enabling caster assembly part and selection. So this is what I mentioned before about the RERC fact sheet that we have created to inform suppliers, users, clinicians, whoever needs this information. And these are just our suggestions from the data we gathered through caster samples in these environments and in our data sources. So for rough terrain, use wide, softer polyurethane and pneumatic tires with a bevel. Smooth surfaces, you want to use more narrow tires with tread. And if you have more adverse environments, with humidity and whatnot, using tires with greater depth helps a lot with sustaining those throughout that environment. If you go to the next, so lightweight casters that are greater than 6-inch or 120 millimeters, this prevents flutter, which is the oscillation of the caster when it's interacting with the surface with a shorter fork trail. These casters have lower rolling resistance, which you would, if you went to Dr. Ott's presentation, you would certainly have a lot of info on that now. And these are very suitable for beginners. Otherwise, casters that are less than 6 inches or 120 millimeters in diameter, they're less susceptible to that flutter. They provide really good clearance for footrest, and they're very suitable for experienced and active users. And then when you look at the bearings, we suggest precision ground sealed bearings to be used for your wheelchairs that you use with users. They have greater load bearing capacities and tighter tolerances. And we also recommend biweekly maintenance to avoid corrosion, contamination, and degradation, which Dr. Mhatre will be talking about in a little bit. And then next, we have choosing the fork and the fastener. So powder-coated forks with at least a 1/4 inch or 6 millimeter thickness is going to kind of provide the greatest amount of durability in that sense. Spacers between fork prongs and axle bearings to maintain those tolerances to ensure that they're performing the best that they can and taking the load off when needed. Axle bolts with a shank of proper length and avoiding the prong resting on the bolt threads to either thread the bolts or provide a higher load to those bolt threads that could cause them to fail. And we recommend using grade 8 or higher stem bolts of 1/2 inch or 12 millimeters and axle bolts of 5 1/16 inch or 8 millimeters. Now, for wheelchair users, you can use these to understand how it influences wheelchair use and health. Clinicians can use this to make caster selections on user needs and use conditions. Manufacturers can develop or improve designs based on standard caster testing. And policymakers can adopt standards to ensure high quality casters are used to avoid user injury. So the last thing I'll recommend here is similar to what they talked about in that large data keynote speech, is that, this isn't the end all be all. These are our suggestions. And it's very important to first use the wheelchair standard with your client, see how they perform with it, and based on their needs and also the environment they're most likely going to be using it in, making some of these design selections. So yeah, I'll pass it over to Dr. Mhatre again to speak about repair and maintenance.
Thanks, Jack. So changing gears here to maintenance now. So one of the things that came out of the repair registry is service repairs. So when I say service repairs, as I mentioned earlier, these are the servicing for caster that happens when the technicians went out for repairing or replacing another part. And so if we pair this, or if we correlate this with the high risk caster repairs, and now this should not be high risk caster repairs, this is high risk caster failures. These are the high risk failures where the caster failure can cause a person to be injured or left stranded. So this is adverse consequences. So if you look at servicing versus high risk caster failures, we see that there is a negative correlation. This graph is not the best resolution that I'm showing you, but if you can look at this downward trend or this negative correlation, that's what I wanted to point out to you. So this is from hundreds of service repairs and high risk caster failures that we are seeing this negative correlation. We have also seen some of this in earlier studies that have looked at preventative maintenance. So we know that preventative maintenance is very important in order to avoid high risk caster failures. However, if you're looking at some of the maintenance tools that are out there, they are encouraging preventative maintenance, and we have two of these which are looking at inspecting, checking caster and as well as other wheelchair parts on a specific time interval, like weekly, bi-weekly, monthly. We have these for manual and power wheelchairs. One of the big things with these things is that they cannot indicate to a user based on usage when the high risk failure is going to happen in the community. If you look at other industries, if you look at the auto industry, you have odometers on cars that are telling you when you should replace your oil, when you need to replace your oil filter. You also have that for the air industry or the aero industry, where depending on how much vibrations do condition monitoring systems see, you need to replace some of the electronic panels or do some soldering again. Similarly, in the heavy equipment industry, you have condition monitoring units for making sure that there is no downtime. So that this is happening in other industries. But when it comes to wheelchairs, we have validated tools that cannot tell us when something is going to go wrong with the wheelchair. And so based on these experiences, these benchmarking to the other industry technology, we are developing WheelTrack, which I call it's as the Fitbit for wheelchairs. And here we have a small sensor that can mount on any wheelchair at the moment, and it connects with the app that we have developed and we are validating at the moment. What it does is it measures some shocks and some other factors that tell us how the wheelchair casters and the wheelchair rear wheels are wearing down in the community. And whenever a maintenance event is due for the user, it is going to go ahead and send you a notification that you need to change your caster part. Very quickly, we are doing some research with WheelTrack. The big research goal for us is to establish this feasibility of predicting maintenance repairs. And even before that, we want to predict when these failures are going to happen. So what we are doing is we are doing 3 primary data collection studies here. We have about 100 people to go. We have this study going on in Pittsburgh and Mexico. There are 2 big aims. I'm trying to correlate the shock failure, try to investigate the shock and failure correlation. So this is shocks, how many shocks we are seeing and what are the failures that are happening specifically with casters and rear wheels and other critical parts. And then can we correlate this wheelchair's condition to the user's health? And so we are using the FMA tool that has been developed at the University of Pittsburgh, so that we can we predict users' health based on wheelchair's condition. We have based on some of the results that we have got, initial results that we have got from this, we are learning that the user is getting stressed when the caster is swiveling or when it is fluttering out there in the community. Some other initial results are that that whenever we are seeing a user who is having twice the number of shocks than an average user in the community, that user is seeing a caster failure within a 1 year's time period. So those are some initial results, and I'm going to save the big study. We were still supposed to do all the 100 users, but I'll save some of the results for the next ISS here. Very quickly to wrap up, so 6 resources that we have developed. We saw the wheelchair design considerations document, selection guidelines. We saw the standard. Now this is not ISO DIS, this is the FDIS now, and the standard should be out there soon in April of this year. We have some testing documentation that we have deployed so that you can develop these tests out there, and you can use these materials to develop new testing machines. We have provided design improvements to the industry on several casters and wheels. And then wheel track is something that's a new maintenance technology that is coming out from this work. Some of the future work in the 4 areas. So the first one is product testing or quality testing. So we want to develop more quality testing evidence and really want to understand, based on what results we got, do we need to tweak the caster testing protocol, or do we need to change do we need to really go ahead and change some of the caster design? So we have done that to some degree, but we still want to keep on establishing some more testing evidence so that we really can have a robust protocol that can that at least can prevent some of the high risk caster failures that are happening out there in the community. We would like to provide some industry testing services, which we are doing already. Design wise, we want to develop some more caster designs and develop them based on some of the testing evidence we have got. The next stage for the bushings related development is, can we 3D print them? And then like you have 3D printers that are out there in the community, you can use them to 3D print, especially in remote areas where access is difficult. So we're looking at something like that. We're also looking at something like dust testing, because we know that dust ingress, dust entry into the bearings is a big problem, just like corrosion. Caster selection, we are developing a list of parameters that can be help for selecting casters. And so I don't want to dive too much into what these parameters are looking like, but we can develop a caster selection tool which can be used by clinicians when they are prescribing or selecting casters. And then preventative maintenance, wheel track wise, we are developing this correlation model, as I mentioned, and then we're looking forward to developing an intervention where you can do preventative maintenance with wheelchairs in the community. These are some of the references. I see that some of the references are omitted in this one. We have selected a few. I'm happy to chat about some of the work that we have covered today. That's all from. What was that again?
Oh, I was just going to say, I also added, for instance, the paper we released on the wheelchair repair registry to the ISS, like our section on it, and as well as some of the other, like the fact sheet and the design considerations. I uploaded those to our section.
Okay.
For you guys to see.
Thanks, Jack. Mm-hmm. And that's our presentation, and I look forward to some interesting questions.
Thank you, Anand. Thank you, Jack. Excellent presentation. Lots of content that you've covered. We have a steady stream of questions coming in, and you can both, I think, address them one by one, starting with the first question from Larry Raymond. If Anand, you could please just read out the question and then your response. Thank you.
So the question is from Larry Raymond is, how about lateral forces, like when the caster gets stuck in a gap casing, a lateral torque, and impacting the bearing/bolt interface? So Larry, that's a good question. We have done a study like this with the casters. What we are looking at is, when I showed you the caster test machine, and take you specifically on this page right here. So when we developed this one, a part of the reliability testing study on this one, so we wanted to make sure that these casters are tested reliably. That is, to some degree, we wanted to do that and also establish the internal validity of this test. What we did is, in that study, we had these obstacles hit the casters. At the same time, we had these obstacles be at an angle at a 45-degree angle and come and hit these casters. So there was this comparison testing study, and you can see that study in this reference at the bottom here. What we found is these bearings are taking some of the extra load or the hit that is being given by angled obstacles, and it is not affecting the durability of a caster. So that is what we found. So we did not find that lateral forces are making any or angled forces are making any impact. On the other hand, lateral forces, we have not looked at anything that is impacting the caster laterally. I think that may be another testing method that you can look at. And again, we need to first go out there and collect more data on what that lateral force looks like before we go ahead and develop a test for understanding how this lateral force can affect a caster. But a good question. Thanks for asking that.
And I can answer these next two from Carla and Douglas. So Carla asked, does the comparison with the community data suggest that lab testing need to be adjusted in order to reflect more of the real world? That's a great question, Carla. I would say in terms of time to failure, we need to see, because of course it varies from model to model, but the more data we collect, and once we have more of the ultralight, I think we'll have a more robust understanding of where the time to failure is for the lab based on what we're seeing in the room. The failure modes are matching very well, but we just need to see kind of an overall look, and then we can kind of hone in whatever that value is, whatever the correlated value of it to make it more reflective. So certainly we need to, possibly depending on all the data we get, change what our definition of an equivalent year is, or whatever we want to do to make it a more robust, accurate measurement on the lab test.
Yeah. Jack, can I add here one thing? So
sure.
It's a good question. Do we need to change the lab test? I don't think so at the moment we need to change the lab test. The big reason for that is we did the tilt in space wheelchair testing without going and understanding how this load is on the tilt in space wheelchair.
Right.
So we did the testing under a standard load, under standard conditions, but it may not be the same way it is mounted on a tilt in space chair. So we need to get that data and integrate that into the testing, understand how that loading is before we make a decision on should we change the lab test. We are getting promising results here, but I think still some data needs to be there for backup of the test method. And then we can conduct that test and find out, okay, do we need to go ahead and change the lab test?
Right. And I think that kind of relates into what Dr. Kuntz had asked, discussing the effects of user load on caster performance, how it can inform wheelchair setup for frame design. So like Dr. Mhatre said, we are working to figure out, how that changes across the different wheelchair types and what that looks like. So that's another, change we can make to kind of hone in those values.
The caster standard, what it does is, the caster standard asks the manufacturer to specify the load on the caster. For us, when we are doing this testing study or research studies, we are applying a standard load of 30 pounds on top of this caster. So it may not be the same when it is mounted on the wheelchair. So what the caster testing standard does is it is asking the manufacturer to state that, so that we can, if it is like for tilt-in space chairs, we know that most of the load is on the front casters. So we want to see what that load is. Probably it's 60 pounds. We don't know, but that can happen through experimentation and more data collection.
Right. And Douglas Robbins asked here, although you may not have tested it directly per se, do you have a feeling as to whether the thermoplastic bushings had a greater rolling friction than ball bearings? So yeah, great question. We are currently in the process of publishing that study. And what we said in it is basically that, yes, we have not tested outright the rolling resistance. That's what we would like to do in a future study using the testing equipment that Dr. Odd has developed, testing those casters to see what the difference is in rolling resistance. Basically the same exact study format, just using that testing equipment instead. Very interested to see those results, but if I could guess, and what we say in the paper is that the if you go to the results, if you go to like the failure results, there's a lot of there's more. Sorry, next. Yeah. So it's harder to see in these photos, but the tire wear on the ball bearings, both these models, is much higher than what we saw on the thermoplastic bushing, which might have been a reason for why we might be able to say that the thermoplastic bushings might have a better rolling resistance. Whether that's true or not, we're going to have to, actually test and find out. But if I had to take a shot, that would be kind of my reasoning to show why it actually might be better rolling resistance.
Jack, can I add to this? This is a good question. It is true that there is greater rolling friction with thermoplastic bushings. So when you start rolling this, the starting friction, definitely it's larger. But once it starts rolling, in rolling, I don't know if you call rolling kinetic friction, that friction should be similar to what we see in a bearing. We do not know this. We do have a rolling resistance testing machine and we can find that out. But I think that's something in the works, and we'll find more about friction and thermoplastic bushings.
Thank you, Anand, Jack. I think most questions have been addressed.
I think there is one more question from Carla.
Before we get to that, Anand, I'd just quickly like to share the CEU code, because we only have a few minutes left, and then we can get to your response. The code is AS6BRV. It's also in the chat window here, AS6BRV. That's Alpha Sierra 6 Bravo Romeo Victor. Anand, please go ahead.
A direct answer for Carla's question is yes, we are looking at distance traveled for predicting. It's there as a part of the sensor that we have developed for wheel track, and we do not know at this moment. Again, we have not analyzed the full data if distance traveled is correlating with the failures that we are seeing, but we know something about the shocks that's happening. I think it's the analysis is ongoing, and so I think I'll talk more about this work that's there on wheel track in the upcoming conferences as well as the next ISS. But I think there should be some correlation between distance traveled and failures. We are already seeing some of that. I think Carla, you presented this yesterday. We are definitely seeing some of this correlation between distance traveled and failures. So more to come. I see one question from Jackie Macaulay. Would caster suspension have any impact on caster failures? Jackie, there is a testing study from the Human Engineering Research Labs a long time ago. It showed that the suspension had no impact. On the other hand, it found that the suspension had less durability when it comes to how it works. So it was a reverse effect, which was quite weird, but it probably speaks to the durability of the suspensions that are used in the community. But yeah, that's the answer for that question. We have not tested suspension forks at the moment on the caster test.
Thank you. We see a lot of comments just thanking you both for your presentation. So Anand, Jack, thank you very much.
Thanks everyone.
Yep. Once again, the code is AS6BRV. We'll stay online for another 1 minute in case any of you have a question, and then we will end the session.
We did pretty well on timing.
$53 slides, right?
Yeah.
Okay.
Good minute to slide ratio.
Okay. I think we can stop the recording.